Okay, folks, let's get started. Thank you very much for coming along after lunch and already a long day of learning. I really appreciate it. So in case you haven't read the title of the slides and looked at your agenda, you are here to learn about data science. I promise you, no walls of maths today. Okay? So we're not going to make anyone's brains bleed out of ears. So a little bit about me. Hi, I'm Steph. I run a data science consultancy and an AI readiness software startup because one business is just not insane enough. I'm mostly a data scientist. I spend a lot of time working on the operations side of data science. A lot of people can do super duper awesome 99.99% accuracy models. I actually make those things go into production, because if it's not in production, there's no point. I do have a bit of a Microsoft slant. Microsoft Azure is nice and easy to get on board with, so and I present a lot inside the tech communities there. So I will include a bit of how Microsoft and Java can work for data science, but I promise to not be too biased. And do stay in touch, so Twitter and email. If you have follow-up questions after this and you don't get a chance to ask them, or you only remember them on the train home tonight. Okay, so first of all, going to go from top to bottom. We're going to go from what data science is for, through, and then into kind of at the last point, what the tech kind of architectures look like. So data science is solving problems using data you already have. We use models, which are a way of simplifying lots of noisy information like 8 million customer records, and building a representation of how they engage with your product, for instance, so that we can then say, since these people engage this way, if we change this business process, we will get an uptick in profits. Okay? So we're looking to understand how systems work, how people work, and how we can change things as a result. So we might have Amazon as a classic. They have all of our purchase history for almost everything we buy these days, and they're able to say that people like us who buy the new kitchen gadget also want these other kitchen gadgets. So that's a type of data science product called a recommendation engine. There's lots of these different algorithms and processes that are in place using data that we are generating and usually providing to companies. So where possible, we solve real business problems, whether the business is curing cancer or helping people stay in a telecoms mobile provider for longer. Okay. Usually areas where if you want to suggest a data science product to be kind of starting with, things like reducing overheads. You can use data science to work out how to better reduce IT spend. We can cut down on wasted food if you're kind of in a retail or a catering sort of situation. We can help you work out new products. So you can look at customer segmentation and how your customers interact with your product, work out where it's weakest, and design products specifically for those people. We can help with conversion problems, so understanding A/B tests at scale is a common data science task. We can help with retention by identifying the customers at most risk of leaving so that we can do things about them. And we can help upsell and change the way that people interact with our products so that they buy the more expensive or more profitable version, or they add some extra pieces on. So with data science, we're usually looking to sit inside an application and actually improve or build upon a business capability. Ideally, we're not going to sit there in the corner and tune on neural net all day. Okay? Business value. And we do that by sitting inside that business process, and we're looking for an understanding of how something happens so that we can predict what will happen if we make a change in our systems. So if we have a call center application and we want to make sure that the customers most at risk of leaving are better treated so that hopefully they stay, we have a model that works out customers who are most likely to leave, and then that sits inside the call center application so that when the person rings through, it checks their likelihood to leave and routes them to the best customer services person for them. Okay? So we usually sit inside a process. Okay. When we build data science products, we go through effectively a software delivery lifecycle, but our software delivery looks a little bit different. This has been hard to beat since '96, the CRISP DM process. So this is a data mining process for describing how people go basically about building data science products. And if you're like me, you'll be quite cynical. It's statistics, data mining, machine learning, AI, data science. Most of these are just doing the same thing, taking somebody's data and building some sort of model out of it that tells us information. So if I use one or the other of those, or you have a background in one of those, you can do data science. So we start off with that business goal. What is the business process and the business challenge that we want to solve? We then radically go into understanding the business. We start thinking about, how does this process work? How can we engage? How can we put an intervention at a specific stage? What possible other impacts will there be? Do we need to consider ethics? Do we need to consider that it might have impacts on other key business metrics? Will data be available at the point of this business process that we can make changes? We then go into data understanding. What kind of data do we have that we can use and that we think is predictive for this solution? And these have little circles because you might go, oh, this data probably isn't good enough. Let's go back to our business understanding and check things out. So we have iterations that can go backwards because we can fail. Not that we can fail, but that we can get new understanding. That means we have to go back and refine an earlier understanding step. Once we believe we've got the data all sorted, usually data scientists love the CSV. The big flat file is our friend. And so actually when I do a lot of my talks in the data science community, I start teaching data science people SQL and databases, because databases are, good and there for a reason. But when we build models, ideally we want one row per thing that has an outcome. And I'm talking mostly about things that we have known outcomes for. Because usually in business, we have something we want to try and predict is going to happen. Okay. So we get one row per thing that happens, and we get a whole bunch of columns that might impact the thing that we're trying to predict. So for customers and whether they're likely to churn from your company, you could look at attributes of the customer, attributes of their usage of your system over the past X months. You can add information about about your competitors' offerings for them. You can get information about their socioeconomic demographics. So we can grab all of this information, and you basically end up with a really wide data set of possible columns. We then go into the modeling phase, and that's where we apply algorithms for distilling that wide and tall data set into something that is much easier and is basically a complicated rule set. Ideally, we end up with something that you can write that somebody in customer services can understand, or you can at least explain for GDPR purposes. We build a bunch of these different models because you can't guarantee which type of algorithm will produce the best outcome for your data. We then evaluate those models. So we work out which ones are best from a number of business success metrics and kind of some statistical measures. And we check and make sure things like, do they actually work on our high-value customers? If our model sucks on our high-value customers, why would we put that into production and risk driving all our high-value customers away? So we test on things like accuracy. We test on ROI, like how much time are we going to spend getting this into production and how much extra money do we think it's going to make us? And we test against key segments. Then we deploy it. So usually that takes a model that might be a representation that says if the customer is from Scotland and they've spent more than 10 extra pounds over their bill in the past 3 months, and a competitor has just released a cheaper iPhone plan, then they have a high chance of churning, so do something with them. Give them a voucher, see if they stay. Send them smiley faces on a daily basis by text. Do something. And that requires that scoring set of rules that we come up with to sit somewhere in production. So that could be inside your application, it could be in a separate API, or it could be something that sits in your database, or even if it's a batch process, you could have like a standalone virtual machine that runs a script once a night and adds the results to your database. Whatever way gets it into production as quickly as possible and in a sustainable way. And then you monitor it. Anytime we build a system or change a system, it can have adverse consequences that we don't think about. Nothing's ever perfect, so we need to check for errors as well. So we need some sort of solution where we can actually see what we're predicting, what we base that information on, and what was the outcome for the business. Then usually we'll go through that whole cycle again to refine the solution. So the CRISP-DM model, work is never done. It's like sprints. There's always another sprint afterwards. Okay. So what skills are needed if you want to do data science? We're finally at a point where most people are not asking for unicorns. They're not asking for somebody with 5 years software engineering experience, plus a PhD in machine learning, plus 5 years of business analysis and data visualization experience, plus 5 different coding languages. That person is pretty rare and consequently very high priced to get, but that doesn't scale well because they're rare, because they usually, they're too busy doing everything to play nicely with others. So we can start splitting these skills out and make data science kind of more of a team, cross-functional team structure. So usually the kind of functions that you need inside your data science team, you need somebody with data wrangling skills. You need to be able to usually communicate with databases, APIs, spreadsheets. You need to be able to build joins, add columns programmatically, develop aggregates. You need, and most importantly, usually clean the data up. So you need somebody who can wrangle that data. You need somebody who can do the modeling, who can take that wide data set that the wrangler has built and actually build a model that works for the company's goals. You need coding skills. You need to get this into production. This might be putting it, as I said, inside a discrete API, embedding it inside the application or in the database, or as a batch process. All of these will require some coding and usually some change to the production system. And then you need communication skills. There's a lot of high jargon concepts and theories and working environments and things in data science. And if you can't talk to the stakeholders about the value that you're adding, the caveats, the health warnings, and how the solution is working, they're not going to trust you. They're not going to trust your outputs. And then all that time will be wasted because they'll just ignore the answer your model is coming up with. So communication is really important, and particularly for ensuring that you're tackling the right business challenges, getting a good understanding of the business processes, and for that trust. So you can actually have like a data engineer, a machine learning engineer, a software engineer, and a business analyst, or a business intelligence specialist. And this would be your data science team. Because usually the bit about modeling is less than 20% of the workload that a single solo data scientist will do. So if you can split up the data science work, that is really helpful. And it also ensures that your bus factor doesn't cripple you. Because usually I see a lot of organizations who will just hire a solo data scientist. Often the data scientist will come in, realize that the business isn't quite ready for them, and get annoyed after building like one production system and bugger off. And all the knowledge goes with them. So having a team really helps keep a lot of the knowledge inside the organization, because you'd have to be pretty bad to make 4 people leave rather than making 1 person leave. Right. We're at a Java conference, so Java is not a data science language, primarily, right? You can do data science in Java, but you're very much off the beaten path. Core languages are Python and Scala and Spark. The plus side is that if you want to pursue data science more in depth, then we actually have some solid learning paths for how you get there, some specialisms. So Scala, Hadoop, and Spark, they're all JVM based. They're all strongly typed languages that are Java situated. So you can specialize in coding in these high-scale big data type of technologies. The other area that is often in demand is software engineering and actually operationalizing data science, turning a theory into practice. So that is a valuable area and extends into NLP, natural language programming, where we can start doing text analysis and things at scale. So these are the two kind of learning areas that I would recommend if you want to progress this as a potential career. Your Java skills are still valuable, but put them into the JVM-based languages. So how to succeed at data science in an organization? Can't have good data science without good data. Data quality is a business an executive level strategic impediment, and therefore an opportunity. Something like 80% of organizations have had data and software projects stopped because of data quality issues or slowed down. So if you're one of the 20% of businesses where that isn't the case, you're going faster. And if you're going faster, you're making money sooner. So get good data and be conscious of this all the way through the process. For your first project, you want to start big, but not too big. So you've got importance and impact. You don't want something that's completely trivial for your first project, because if you're going to dedicate usually extra time than you thought you would to the project. So it could be like doing facial recognition inside your application, for instance. You decide to not buy off the shelf, and you spend months on this project, and somebody goes, oh yeah, but we could have just put an API in, or just asked them to phone us. And people would see that it had low impact and wasn't that important to them, and they'll dismiss your work. The other extreme is you pick something high impact and high importance, like how much money the bank should hold against a downturn. And then a downturn happens, and it turns out you really screwed up. Right? You don't want that kind of thing where you accidentally topple a key banking player. You want something that's kind of in between. Something that's important enough that people go, oh yeah, we should continue investing in this type of thing. But not so important that if you screw it up or the project doesn't deliver, that you're not all going to get fired and the data science ground salted forever. Okay? And prepare for production. The model is the teeny tiniest bit of a data science solution. So you've got feature engineering. The data scientist, or you're going to go and add a load of extra potential columns based on your data. You're going to need those values to actually be there in production. So if somebody has, for instance, like the average monthly minutes per use over the last 6 months in the model, how are you going to get that inside the call center application? If you can't get that in the call center application, then that can't be in the model. So we need to be able to make these values happen in some way. So we need to make them. We need to be able to do the monitoring and the logging. We need to do regular retraining. So with most models, we assume that the past performance is a good indicator of future performance. The trouble is, the further back you go in the past, or the further you go trying to predict in the future, the bigger the challenge you have because behaviors change. So what we regularly need to do is, instead of our model being based on old data, we need to regularly take the latest set and reconstruct our model. And that means then we need the compute power and the ability to get that nice big wide data set regularly performed, And we also need a way of shipping the results into production. And a lot of data scientists still haven't heard about DevOps. So we really need, that often goes forgotten about. We need to think about compliance. Are your data scientists seeing production data when that's not contractually allowed? Are they working with personally identifiable info? Is this potentially ending up embedded in the model? How are you going to deal with the right to be forgotten? We need to think about these things. Security. How are we going to ensure that people can't game our model? So, how are we going to respond to adversarial behaviors to prevent how our kind of custom IP that does like risk pricing doesn't get spammed by our competitors enough so that they can work out what's important in our model? You need to think about how you secure the model. And then A/B testing. Like with anything, things that we think will often have a positive impact at the time we're thinking about them and building them don't always have that impact in production. So if we should be testing our model. If it's our first model, we need a control group. And then if it works, when we go to build subsequent iterations, we should be checking to see if the new one actually beats the old one in a substantial way. So we need to be applying the same sort of techniques to large experimentation on the website into our modeling solutions. Okay, let's look at how some machine learning works. And we're going to start with a linear regression. Because machine learning companies and stuff will do a linear regression and tell you it's machine learning. Technically it is, but it's not that fancy. But it's often one of the most useful solutions. So what we're working with when we do a linear regression or a line of best fit is we're basically saying that there is a linear relationship, so a straight line relationship, between the columns in our data set and the thing that we're trying to predict. This is an assumption, and all models end up assumptions. They just might end up quite detailed assumptions about how things work, because there's simplifications. So we have our x-axis and our y-axis, and we have some data. And the nice thing about the really simple case is it's basically y equals mx plus c, which is our line of best fit that we did when we were younger in high school. And we have m, which is our unit of change here. For every one movement across the x-axis, how much do we change our y-axis? That's a coefficient. And then we have c, which is our intercept. So where does our model think we start off without any other information? Okay. So regression, or linear regression, is basically a line of best fit. It has an algorithm for coming up with that best line, but it's a line. There just might be lots of dimensions that we're trying to draw a straight line through. We have a couple of concepts that we need to think about. Bias and variance. So bias is where our model doesn't work in a certain area, where it doesn't have enough information to accurately reflect what's happening inside the data. And variance is where we get error relating to the people or to the things that we're observing. So we're generally capturing the line reasonably, but we still get error to do with people because the squishy bits in the system are the hardest bits to predict. So when we build our solution, we'll look to see whether there's bias in certain areas that might have negative commercial consequences, and we'll be looking at variance to see if this has any specific reasons for. The next bit that you need to think about when you build models is the loss minimization function. So an algorithm is there to simplify a bunch of data points into a rule set, like y equals mx plus c. And it tries to work out what the m is and what the c is. How we do that is we try and constrain towards an ideal value. In the case of linear regression, the ideal value is 0 error. And we start working that out. I didn't quite draw as much as I'd like on this. So each of these values is the error from the prediction. In some cases, it's really large, and in other cases, it's small. If we were doing really well, all of those error values would be small. But there's things like outliers and stuff. So the way that the algorithm could work is it could try lots of different angles and intercepts and sum up all of the errors and use that as the loss and go, when I can make this loss as small as possible, then I know I've done a good job because I have condensed the information down as much as possible in a robust way. The problem is we've got positive errors, so where we underpredicted, and we've got negative errors where we overpredicted. If we just sum up the positive and negative values, we could end up with a value that's very negative because our line really overpredicted. Or we could end up with a very positive value because our model underpredicted consistently. Ideally, you want it underpredicting and overpredicting around the same amount. But the trouble is, we could have a couple really big values of overprediction and a lot of underpredictions, and they could sum up to 0. And if they sum up to 0, the model could still be rubbish. But we wouldn't know because it cancelled stuff out. So what we do for the loss function for regression by standard is we actually square all of these error numbers. So a number times itself is always a positive value. The great thing about that, then, it means that as we get closer, the value can never go below 0. And the closer to 0 it is, the better the fit of the model. So it becomes much easier for us to test and our algorithm to optimize our model because it fits towards 0. But that has a consequence on a couple of things that we would then need to think about when we build our system. So if we've got all of these outliers, square numbers get larger pretty quickly. So if you underpredict by less than 1, you get a decimal times a decimal, which makes a smaller decimal. But if you've got a big error term, so basically you have a value that's a big outlier, that might contribute a very big number. which means that our line will start trying to best fit our anomalies, our outliers. So then, because of a consequence of the maths behind all this square stuff on the loss function, we need to be able to build in defensive checks for checking things like outliers. So the different types of algorithms will have effectively different weaknesses and strengths. They support different types of data and different relationships better, and the loss functions and the way that they optimize are sensitive to different conditions. So it's important when we start on the evaluation as well as the data understanding that we check for these kinds of issues, because it would be much better if we took these out and it would be able to better optimize inside our main data set. Roughly make sense? Yeah? Okay. So that's our linear regression and how ordinary least squares regression works. Okay. You can understand ordinary least squares regression, then you can start working on the complicated stuff, but it builds up. You always have how it fits the line, and this might have some parameters for the algorithm for how the algorithm decides what's good or not. You have a loss function, which gives it a target for solving the equation, essentially. And you have the structure of the model that you end up with. So not everything fits a linear regression. Our data doesn't actually have necessarily a straight line relationship. It has potentially what's called a polynomial relationship. So it gets squiggly. And this ends up a little bit more complicated. So as well as our x value, we essentially have a third axis of our x squared value, and we try and fit the straight line through both the x-axis and the x squared axis. So you get two components inside your regression. This helps us get to something that's quite accurate, which is useful, right? But you can make it very complicated. So you can get something that gets more and more specific to your data that you're using inside your model. You might get so specific you learn most of the details about your x-axis, or the 10, 50, 100 columns that count. And it gets so specific, so detail-oriented about the customers you already knew about, that when it starts seeing new records, new customers, it doesn't work anywhere nearly as effectively, because it says, like, hey, you're not like John down the street. Why aren't you doing what John did? Well, like, I live down the street, but I'm not like John. So this is the challenge that we go through when we build models. We're looking for something that fits well, but doesn't fit so well, it doesn't generalize when it's in production. So again, in kind of our defensive programming for data science, we take our initial data set. We usually split it up into multiple chunks. We build our model on only a part of that data, and then we test it on data it hasn't seen before, but thankfully we know the answer to. And we can see if it does all right on that data. you would usually expect a small drop in accuracy because you usually can tend a bit more towards overfitting for the data you train on than the data you've never seen. A little bit of accuracy drop is fine, but if it drops like 10, 15%, then you know you've got too much overfitting in your training set. So we use actual real data sets and data points inside it to defensively program our models. And most of the data science process, even though it has a lot of mathematical thinking behind it, it's mostly critically thinking about how can I build something that is so over-engineered that it doesn't actually work in real life. So it's how do we make sure that the data is good quality? How do we handle values when they're missing? How do we make sure that when we build our line that we don't end up with something that's hopelessly rubbish and doesn't work or is too specific? So we end up with kind of like a checklist of things that we can do. So what do the sorts of implementations for data science in production look like? So you can have real-time personalized offers. Okay. So you might start off with a user clicking on your website, and you want to show them some coupons or some offers or some recommended content that you want them to see. You might use like Lucene or something to build a search that returns content to the front page, or you might have like a rules engine where on this day, if this person logs in, show them this type of content. The trouble is maintaining those rules takes a long time, and that search index might not be easy to weight towards attributes of the customer. So what we can start doing is real-time having a model that makes a prediction. We have an issue with cold start. Like applications, that usually takes a warm-up time for us to get data in, particularly for new customers, to be able to predict effectively for them. So we need basically our fallback. If we don't have enough data to have a good stab at this in production, what are we going to offer them? So your Lucene or your rules engine could still be there. If we have enough data, we can then send that data to our model to say, hey, this person, they're like from Scotland, and they have this type of phone, and they're in this socioeconomic demographic. What should we predict for them to see on our news page for our phone? And then we'll get a prediction back, and we can show things on the front end. We also start sending that data between what we showed them, the information that we had about them, and the responses we gave back, plus ideally their results. Did they click on a page? Did they share it? Did they bounce immediately? We have a bunch of pieces of information that we can then store to be able to refine our solution. Queues are great for helping build scalable solutions, whether it's Kafka, Event Hubs, whatever. They help us buffer data so that we can cope with changes in volume. So we're using here Azure functions, but this could be, which do support Java. I was happy to find out that. But they're basically any microservice or endpoint inside your application. So you can build this sort of solution without necessarily doing the asynchronous queuing inside your existing application. But the main thing that would be potentially new is your scoring API. And that can be delivered black box in any programming language that your data scientist or you wants to code it in. You can be working at scale from kind of working on telemetry. So you'll usually get your data coming in, streaming. So you might be, anybody using like Node-RED to analyze IoT data? Anybody doing IoT? Cool. I get to skip that. In the Microsoft stack, we have a number of levels of capability. So if you don't have any data science function inside your organization right now, and you don't have the time to go through learning about these things, playing with them, building the prototype so you get your head around them, and going through the learning curve of kind of going into production for these things, Microsoft, Google, AWS, Algorithmia, a whole bunch of other people have data science products as a service. You can score extra brownie points by calling them AI. But we have things that do image detection, video indexing, speech to text and text to speech. We can take text apart and identify the people and the landmarks and the relationships between them. And of course we have search, and the search can have some of those cognitive capabilities in as well. So those are APIs that you can just get started with. If your application is allowed to talk to the internet, great. You can go and call that API. And in most of the cases, they actually have Docker containers that you can bring into your organization that keep all of your data on-prem versus going into the cloud, even if it's on your own storage and kind of area of Azure. You can customize those as well. So it's really easy. If you want to play with deep learning image recognition, go to customvision.ai. And I did this with like 200 pictures of my dogs. You can get started, upload a bunch of data, a bunch of images, tag them, it'll train it, and you'll have an API that has a custom solution that is trained on your business data or your dog's data. You can then start getting into hosting models. So there's .NET, ML.NET, which uses TensorFlow models. Onyx is an open neural network framework that can compile neural nets on a variety of devices and compute layers. So you can run models that you've built, and you can go and run them on any, like even something with an ARM CPU. So you can be putting them in edge devices, which is pretty handy. You have your development environments for data science products. So Databricks uses Spark, which is the Scala data, primarily Scala for data science. Azure Machine Learning Services gives you a framework for recording your artifacts as you go through the process, which is important from a compliance perspective if you do any financial services or health data or anything, you're going to want that kind of audit framework. And then they have a bunch of sandbox machines with everything pre-installed. So you never have to go through the pain of trying to get Apache Drill to run on Windows or something like that. And most of these models work. All of it's kind of interoperable. So you can have it working inside your on-prem solutions, you can integrate to the cloud, and most of it you can actually embed in your IoT as well, which is pretty cool. An area that's really helpful and is in Spark and Databricks is Delta Lakes. So anybody heard of data lakes? Anybody think of them as data swamps? Yeah. So data lakes are data schema changes mostly quite frequently these days. We're always adding another field into our application, and we need to get that through into something that analysts and data scientists can use. But database changes are hard. And changing the operational database and the ETL that takes that into a data warehouse based in like Oracle or SQL Server is cumbersome and takes a lot of time. And we often end up losing some information along the way. So the idea of a data lake is we just basically start dumping the raw data in at the end. In is kind of like at the river's mouth, source. And we get the data in, and then we do processes of refinement until we have nice, crystal clear, drinkable data at the end. The problem is that it fundamentally relies on documentation and communication and standards. If we were good at all three of those things, there'd probably need to be fewer IT people. So we tend to end up with more of a data swamp than a data lake, but it is very useful conceptually, and particularly when you start doing a lot of data science at scale. When you're building more and more new features, new additions to your data science, to your data set. So the Delta Lake, previously with data lake sort of solutions, you would have to write the whole file in. So you might have to write like 1,000 customer records in one go. And then you would batch process those 1,000 records into like the 500 records of interest and the 250 and so on. With Delta Lakes, we're able to start working on streaming data as well. And we're able to put CRUD operations, create, read, update, delete, on our tables of refinement. So this allows people to start doing streaming feature engineering inside a solution that works on a JVM, sits inside your cloud environment or on-prem, and enables you to do scoring on the other side of it or through that process. So the Delta Lake is a useful addition inside a Hadoop stack that can help us simplify at least some of the data storage and management operations. Oops, a little bit over. Thank you very much for not leaving immediately. Thank you all very much. I'm here for the rest of the event, so if you want to ask questions, I am here and more than happy to answer them, but I can appreciate you probably want to go get a drink and cool down. So thank you all very much for coming along today.